because it got a mistake in it.
No,
It's not in the numbers.
it's not so common.
All of the calculation is fine. The mistake is in the problem statement. That should be copper sulfate and not sodium sulfate. How can I have a copper half reaction if I don't have any copper? Well, everything's all right except that one. That probably prompted your question. Then we're ready to switch gears from electrolysis cells to the other kind of cell. And the other kind of cell is called a galvanic cell. Now, so to speak, this is the opposite. And what is the opposite to what we've just been talking about, the electrolysis cell? In an electrolysis cell, you use electricity to generate chemical change. Here, you'll use chemical change to generate electricity. With the electrolysis cell, you've got to force the reaction to occur. And it's the electrical current that forces the reaction to occur. Now, why do you have to force the reaction to occur? Because it's a non-spontaneous reaction. If this is the opposite, we're dealing with a spontaneous reaction. So to speak, we don't have to plug it in. It's going to go by itself. Now, what direction are we heading to? We're heading to the direction of devices called batteries. You don't plug in batteries. Now let's look at the setup for a galvanic cell then. First item is what I just wrote over there and what I've written up here, a spontaneous reaction. Is used to produce electricity. And now this next item, this is different than the electrolysis cell. I'm giving everybody too long a breaks. They got time to go to McDonald's, but on the break, so now you're making me hungry. So here, a spontaneous reaction is used to produce electricity. The oxidizing and reducing agents are arranged in a different manner. And the oxidizing and reducing agents are A, not in physical contact with each other. And the reason they're not in physical contact with each other, they are contained in separate compartments called half cells. And each half cell contains a solution and an electrode. For the oxidizing and reducing agents, may be in any of four different situations. Can be a solute, which bathes the electrode. Now that's what you'd expect. I mean, the electrode's dipped in a solution, and that solution's got to have ions in it. Those ions would be bathing the electrode. The next one you wouldn't really expect, it can be a gas that bubbles around the electrode. It can be a solid deposited on the electrode. Or it can be the electrode itself. That is a reactive electrode. We'll talk about situations that involve all of these. So we've got two half cells. Each half cell's got an electrode, and it's in a solution. And we got in that solution, you're going to have the oxidizing agent and reducing agent. And 5, the two half cells are connected by a salt bridge. And the two electrodes are connected by an external wire. Now, to get at this salt bridge bit, we need to draw a diagram of a galvanic cell. Let's look at this reaction. Zinc is a solid plus copper ion aqueous to give zinc ion plus copper. What we've got is zinc metal in a copper sulfate solution. So here you got your zinc metal, you put it in the copper sulfate solution. So you got copper ion there, the zinc and the copper ion react. And electrons are transferred, and what happens? The zinc dissolves, you get zinc ion, and the copper comes out of solution. The copper ion is changed to copper, so I mean you got two half reactions. Zinc going to zinc ion, and you got copper ion going to copper. And if you just take a beaker of copper sulfate and you dump zinc in it, this reaction goes. It's a spontaneous reaction. Copper sulfate is a blue solution. And as the copper comes out of solution, the blue color starts fading. And you can see the zinc is metal, the size of the zinc metal is decreasing as the zinc goes into solution. So if you just put this in the beaker, the electrons are just directly exchanging between the zinc and copper species. Again, because it's spontaneous. Well, if you want to get electrical energy, you've got to separate them. You've got to make the electrons run outside through the wire. And so when you set up this cell, we said you have two half cells. And in each half cell, you've got an electrode. And then you connect the electrodes. And in the this electrode here is zinc. And the other electrode is copper. And the copper electrode is in a copper ion solution, copper sulfate solution, and the zinc here is in a zinc sulfate solution. Now, what I've got diagrammed there, that won't work. That's incomplete. For any cell to operate, you've got to have a closed circuit. the electrons have to get back to where they started. Well, we got electrons running around here, but how are they going to get from this beaker to this beaker? To get back where they started. To do that, we use what is called a salt bridge. And you can think of it as an inverted U-tube. And so we've got a tube here. An inverted U-tube. And in this tube, we've got a gel-like substance. And this U-tube goes into the solution. And this allows for the movement of ions. Usually, let's say this gel is a potassium chloride gel. And if you got a potassium chloride gel, potassium ions come out here and chloride ions come out here, and that keeps your charge balanced. You can see here, copper ions are going out of solution, so you're losing positive charge. So you've got to have some positive ions coming back in. And here electrons are going out here, and so you've got to have chlorine bringing more electrons in. Okay, this is what is called a salt bridge. It is a salt is what? An ionic compound. And you got to bridge the two beakers. Now when you do your electrochemical experiment in the lab, when you build the cell, you're going to have to build a very unsophisticated salt bridge to connect the two half cells together. And so here, this reaction here is going right here, and this reaction here is going over here. And that's the general design for a galvanic cell. Now, what's the big difference? In an electrolysis cell, the two electrodes are in the same solution. Here, the two electrodes are in different solutions. Now why? It's a spontaneous reaction. And the electrons would automatically jump from one substance to the other if they were not in the same solution. And the electrons wouldn't go through the wire. You want them to go through the wire. That's your electricity. And so you got to have separate compartments. What's the name we have for these separate compartments? Half cells. And in each half cell there is a reaction going on. And what do we call that reaction? A half reaction. So now we're getting back to the terminology we used for balancing redox equations. What was the instructions on the exam? Balance these equations using the half reaction method of balancing. Now we want to look at a shorthand notation for denoting galvanic cells. We don't want to have to draw out all of the different aspects of a cell every time we refer to it. And let's take this reaction that we're starting with, or we just discussed. Okay, there's the equation for the reaction. Now let's look at the shorthand notation for the cell. Okay, what's happening and what's the rules and regulations. That is the anode half cell. And the anode half cell is always on the left. By definition, it's on the left. Now, anode is what? Where oxidation occurs. By definition, anode is oxidation. By definition, oxidation is loss of electrons. And the zinc is losing electrons to become zinc ion. So this is then over here on the right, this will be the cathode half cell. And this direction here is the direction of electron flow. Electrons are going from the anode to the cathode. Now we got some vertical lines here. We got a line here, and a double line. This is a phase boundary. Here we got solid and aqueous phase. And this is a phase boundary. And the double line in the middle, that denotes the salt bridge. Now, in this particular cell, the electrodes are reactive electrodes. We got a zinc electrode and a copper electrode. And the zinc electrode is immersed in a zinc ion containing solution. And the copper electrode is immersed in a copper ion containing. So this here is this is the electrode. And this is the electrode. Now let's look at cells with inert electrodes. And write a shorthand diagram for such a system. Okay, now in that cell, one of the electrodes is inert, the other one is reactive. One of the electrodes is copper, the other one is platinum. The copper is reactive, the platinum is not. So this is a reactive electrode. And this is an inert electrode. How did I know that the platinum electrode was inert? Over here I'm given two substances, the reactant and the product. Here I've only given one, which means the other substance must be the electrode. So again, two in there, that means the electrode itself is not participating in the reaction. A sign on the electrode, a sign off the electrode. Here I'm looking plus or minus. Is the electrode positive or negative? And the convention for the sign is opposite in a galvanic cell compared to an electrolysis cell. So let's compare the two. A galvanic cell and an electrolysis cell. Now we've already talked about the electrolysis cell. Here the anode is positive, because electrons are pulled out of it by the battery or some other source of electricity. Remember, an electrolysis cell has to be plugged in. Here, the anode is considered to be negative. Because it supplies electrons to the external circuit. In both of these, we still have the anode is oxidation and the cathode is reduction. So we don't change the definitions of anode and cathode, but we do change the sign on the electrode. And one other thing here for the galvanic cell, anions move from the cathode compartment toward the anode. So anions still go to the anode. Now they move towards the cathode department. That's the salt bridge. That's the connection between the two compartments. And then you got the reverse statement of this. Cations move from the anode compartment toward the cathode. The next thing is that we want to talk about is what is called galvanic cell potentials. And we got our galvanic cell operating. So electrons are being pushed through the external circuit. For some cells, they're being pushed with a greater force than others. And we want to keep track of the push. And so here's our schematic. Here we got our two beakers. We got our two electrodes. And the electrodes are connected, and then we've got to have a salt bridge connecting the two compartments. The electrons are going through the external circuit. I said they're being pushed through that circuit, and the push depends on how spontaneous the reaction is. If it's very, very spontaneous, you've got a greater force than not. When you can put a voltmeter right here, and you can read what that force is. We're going to use the term voltage to describe that force. And when you do the electrical chemical experiment lab, you will have a voltmeter, and you will measure these galvanic cell potentials. And so this is really the force with which electrons move through the wire. And this is sometimes called the electromotive force. And that's denoted as the EMF, the electromotive force. And it's measured using a voltmeter. So the EMF, electromotive force, of a cell depends on several factors. And the first one is the nature of the chemical reaction. The second is the concentrations of the species. Makes a difference whether it's 1 molar or 1/10 molar or 100th molar. And it also depends on the temperature. Now the EMF does not depend on a couple of factors. It does not depend on the size of the electrode, and it does not depend on the size of the cell. Now we want to look at standard cell potentials. And we're going to denote these E super zero the cell. Okay, now we're back to what we had with delta H and delta G and delta S. It was what? Delta H super zero, delta G super zero. That little super zero says standard conditions. And the standard conditions in electrochemistry are the same as they are in thermodynamics. And what were the standard conditions in thermodynamics? You got 3 of them. First is 25 degrees. What are the other 2? One deals with concentration. Concentrations have to be 1 molar. And the third deals with gases. And with gases you specified the pressure. And so you got 1 atmosphere pressure. Now let's look at EMFs for various cells. At standard conditions. Now the EMF is going to be what? The reading on the voltmeter that we got in the external wire. Now every cell, every operating cell is going to have a different EMF value. I'll just list 3 of them. If you have zinc plus copper ion, to give zinc ion plus copper, that's the one we've had used in all of the examples so far. The E0 value is equal to a plus 1.1 volts. If you take zinc and put it in an acidic solution, where it's going to react with the hydrogen ion, you're going to get zinc ion plus hydrogen gas. And the E0 value here is equal to a plus 0.76 volts. And a third one, cadmium plus copper, gives cadmium ion plus solid copper. E0 is equal to plus 0.74 volts. Now, what are these numbers I got up here? 110, 76, and 74. That's the difference between two half reactions. In every one of those equations, I got two half reactions occurring. In every redox equation, you got two half reactions. It would be nice if we could set up a table that had just half reactions in it. If we had a value for each half reaction, then we could combine them to get a whole reaction. And all we'd have to do is tabulate the half reactions. Well, we can't measure E0 for a half reaction. If we only got one electrode, the cell won't work. The only way we can get a working cell is to have two half reactions. So we want to look at the concept of E0 for half reactions. Now the first thing is, such cannot be measured directly. So it won't work unless we got two half reactions. And we always measure the difference between the two. Now, what we're going to do is E0 for half reactions can be obtained by a method that we used in 1210, where, and this was when we had the carbon-12 scale for atomic masses. We picked out a reference point, and we assigned that reference point a value. Then everything fell out into place relative to the reference. So E0 for half reactions can be obtained by assigning a value of 0.0 volts to a reference half reaction. And then everything else falls in place. And that has been done, and the reference half reaction involves hydrogen ion. Hydrogen ion and hydrogen gas. Now let's look at the three E0 values that I had on the board a minute ago. What were they? 110, 76, and 74. And so we have E0. One of them was 76, and that was zinc going to zinc ion plus 2 electrons, and 2 hydrogen plus 2 electrons going to H2. That wasn't the first one I had listed. I think the first one I had was 110 volts, and that was zinc and copper. Then the third one was E0 equal to 74, and that was cadmium and copper. And so we had cadmium and copper. Now what is this? This here is the difference between those two half reactions. That's what we measure. But this is what? Based on two half reactions. Now what am I saying? We're going to make a relative scale. By definition, I'm going to assign this a value of 0.00. I had to pick out a reference point. That was arbitrary. But it's been decided that the hydrogen one will be the reference point. Now if that's 0, 0, what does that mean zinc has to be? If the difference between the two of them is 7, 6, that means zinc has got to be 0.76 volts. Now I got the same reaction here. If this is 7, 6, so is this one. Now if that's 7, 6, what is copper going to be? Copper is going to be 110 minus 7, 6. And that will equal 0.34. Now this one's got copper in it. So now we know copper is 3,4. So what does cadmium have to be? Cadmium is 0.74 minus 0.34, and that is equal to 0.40 volts. So out of this, I develop a listing. I've got hydrogen ion going to hydrogen. That's 0.0. I've got copper going to copper. That's 0.34. Cadmium going to cadmium ion. 0.40. And zinc going to zinc ion. That's 0.76. Now I add more reaction into the system, and what do I get? A longer and longer list of half reactions. And the E0 value associated with that. So these evil values so obtained are tabulated in a table called a standard reduction potential table. And here the key is reduction as contrasted to oxidation. All half reactions are written as reductions. Now, what does that mean with these numbers here? What is a reduction? A reduction is gain of electrons. So we've got these four values here. We've got copper, let's take these. So we got these four here. This is a reduction. This is a reduction. This is an oxidation, and that is an oxidation. Those last two involve loss of electrons. Loss of electrons is oxidation. And so I now rewrite my table. H plus and H2 is 0.00 volts. The next one is copper 2 going to copper, 0.34 volts. The next one is cadmium going to cadmium, minus 0.40 volts, and zinc ion going to zinc, minus 0.76 volts. Now what did I do? I flip-flop these two. If I flip-flop them, that changes it from an oxidation to a reduction. If I flip-flop them, I got to change the sign. So now that is the values that you'd find in a standard reduction table. As I said, things are tabulated, and let me pass out a handout now. And this handout is a standard reduction potential table. there's two ways of tabulating these values. Let's look at the back side of the handout first. If we go on the back side, which is the simpler way of doing it, there the half reactions are tabulated in numerical order. The most positive one is the top, and the most negative one is at the bottom. And you'll notice in this table, you should be able to find some of these entries I've got on the board here. I see zinc there is a -7.6. Copper is a +3.4. Hydrogen is boxed there, that's the 0 value. Looks like this one doesn't have cadmium on it. Okay, if you want numerical order, that's easy to find. But you got to hunt for the reaction. If you go over on the front side, here it's not in numerical order, but what is it in? It's in alphabetical order of the key symbol. Right at the top, you got all of the silver reactions, AGs. And so then you want to find copper, you go down to the C's to find the copper half reactions. And so all of this comes then, this tabulation comes from running a whole lot of galvanic cells and getting all of these voltages and then assigning a value of 0 to hydrogen, and then everything else sorts out once you get that 0 value. Now this table here's got a ton of uses. We'll spend an hour tomorrow just talking about this table and the many things you can do as far as uses are concerned. As far as problem sets go, you've got almost all of the purple ones still to do. And as far as the new problem set, the first 4 problems on the new one. So all of the purple one and the first 4 problems on the green one. Start lab at 20 after.